Okay guys, so in this video we'll be looking at reversible versus irreversible processes. Now this is a very interesting area in thermodynamics, and if we can understand some of the basic concepts of this area, then some of our thermodynamics understanding will be quite solid. Now the best way to, I think, to discuss the whole idea of reversible versus irreversible processes would be to look at two questions or look at a few questions under these areas. Now, what I can say from the beginning is that a reversible process is one that is at equilibrium at every stage or at every step. Whereas an irreversible process, right? An irreversible process is one that is at equilibrium only at the beginning and at the end, or only at the first and the last step. Okay? That is for a reversible process. For a reversible process, PV, right, is always equal to nRT. Okay? Whereas for an irreversible process, PV is not always equal to nRT. PV is only equal to nRT at the beginning and at the end for irreversible processes. Now, how would this look in the form of a question? Or how would we do calculations related to such systems? Now, here we have a question. It says, calculate the work done and the heat absorbed in expanding 1 mole of a perfect gas at 298 Kelvin, right? And 1 atmosphere to a final pressure of zero point 0.1 atmosphere along the following pathways, if you whichever way you want to look at that. Now, A is an isothermal reversible pathway, right? Isothermal reversible pathway or process. Isothermal, firstly, iso means the same, thermal is temperature, the same temperature, constant temperature. Isothermal means that delta T is equal to 0, right? Just to break down the question some more. So delta T is equal to 0. Why is that? Remember that delta T is equal to T final minus T initial. Therefore, if delta T is equal to 0, it must mean, right? It must mean that T final is equal to T initial, such that when you try to carry out this operation, you end up with 0. Okay? That's what isothermal is. It's constant temperature. We are not saying that the temperature is 0. We are saying that there is no change in the temperature. Okay? That is what that is about. Okay. So we're supposed to calculate the work done and the heat absorbed in expanding 1 mole of a perfect gas at 298 Kelvin and 1 atmosphere, right? From to a final pressure of zero point 0.1, right? So it's going from 1 atmosphere to zero point 0.1 atmosphere, an expansion, right? So the gas is doing work. It's an isothermal reversible pathway. Okay? Now for such a system, the work done is equal to, right? The work done is equal to minus nRT ln, right? We could write V final over V initial. However, we don't have the volumes. We have pressure values. Indeed, we could calculate the volume values using PV is equal to nRT. And since we're dealing with an isothermal reversible process, PV is always equal to nRT. However, why bother? Why to do so much work when we could easily say work is equal to minus nRT ln P initial over P final. Just work with this one. It's easier because we don't have to convert the pressure values. We don't have to calculate the corresponding volume values, right? We don't have to do that. Just work with the pressure values. Okay? This is the one that would give us the, what I would say, no pun intended, less work. All right? So, let's just put back our formula. Work, all right? Work is equal to minus nRT ln, right? P initial over P final. And let's plug our values in. And a matter of fact, if you plug your values in, it's 1 mole, right? Times 8.314 joule per Kelvin per mole times 298 Kelvin, natural log of the initial pressure, which is 1, over the final pressure, which is 0.1. And I don't have to convert the pressure values to pascals because we have a ratio inside here. If you do carry out this conversion, you will come back to the same thing. And you can check it. Okay? Don't forget the minus sign, which is naturally on the formula. And what you will find is that after your calculations, the work will come down to be, all right, something like minus 5704.82. That is what I got. Okay? Now, since we're talking about an isothermal process, right? In an isothermal process, we just said that delta T is equal to 0. In isothermal process, the fact that delta T is equal to 0, delta U is also equal to 0. And if delta U is known to be equal to Q plus W, the only way that Q plus W could work out to be 0 is if Q is equal to W, but guess what? Equal to W in terms of magnitude, right? But different in terms of direction. One is negative, the other is positive. And so when you put the two together, you end up with 0. That is, if we calculated up here, the work to be, as we have it, 5,704, right? That's the work, minus 5,704. Then Q must be equal to positive 5,704.82. Let's put everything, joules. All right, that is what we have. That is what we have. Okay. All right. Now, let's look at the so we have successfully done our calculations here for the isothermal reversible pathway. Now, what about the isothermal but irreversible pathway in 2 steps? That is question B I'm talking about, right? Isothermal but irreversible path in 2 steps. First, at constant volume, right? Constant volume, don't miss that part, from 1 to 0.1 atmosphere, and then at constant pressure, right, of 0.1 atmosphere to its final volume. Now, you are not asked to sketch a PV chart, but we'll just do that for understanding, okay? So, we have a pressure of 1 atmosphere, all right? Let me just clean this up a little bit. Just clean this one up a little bit. Okay, So the pressure is in atmospheres. Okay. Uh, right. So we start off at 1 atmosphere, right? So it's in 2 steps. First, at constant volume from 1 to point 1. Point 1, let's say point 1 is right here. And the volume is constant. Let's call that V initial. So the pressure decreases from 1 to point 1. Right? Volume did not change. And then the question says now at constant pressure of point 1 to its final volume. Right? V final. Okay. And this, of course, as I mentioned earlier, you were not asked to sketch a PV chart. However, this just allows us to get a little bit, get some perspective on what is going on. So we are required now to calculate the work. Now we know for a fact that the work beneath a PV curve, the area actually beneath a PV curve tells us the work. Okay? The area beneath a PV curve tells us the work, which would be this area here. Let me just outline it. Okay? That's the area beneath the PV curve. Now, as you can see, the length of this side can be calculated from V final minus V initial. This works out to be delta V. Okay? The height of this part, because of course, as you can realize, the area beneath the curve negotiates a rectangle. And how we calculate the area of a rectangle? It is side times side. The length of this side works out to be P, just the pressure, P, which in this case works out to be 0.1 atmospheres. All right? Yes. So if we can calculate the area beneath that curve, then we can get the work. Now it is P, which is the length of this side here, times delta V. Delta V. Okay? And since it's expansion, right? We know it's work done. Work is equal to minus P delta V. Okay? Now, the thing is, we don't have the volume values. We don't have the volume values. Now, this is an irreversible process, which means that right here, which is the final stage, PV is equal to nRT. Up here, which is the initial stage, PV is equal to nRT, right? However, in the middle and the other areas, PV is not equal to nRT. Okay? No. And this is because it's irreversible. This is an irreversible process. Now, this is not bad for us because what this tells us is that we could use PV is equal to nRT to calculate the final volume and also the initial volume, because PV is equal to nRT at the beginning and at the end. So we could use this. Okay? We could use it to calculate the final and initial volumes. But in between the beginning and the end, PV is not equal to nRT and we cannot use it. Okay? All right. Let's go ahead and do the calculation. Okay? Let's go ahead and do the calculation of the volume. Okay. Now, PV is equal to nRT, which means that V is equal to let me write a better V than that. That looks like U. Let's just say now the V is equal to nRT over P. Question is, if we want to calculate the initial volume, which one of the pressure values should we use? Which pressure value should be used? Okay? The initial volume, well, it's an expansion that we're dealing with, right? And so the initial volume should be smaller than the final volume. There's a relationship between volume and pressure. And there's a law which tells us about this relationship. It's called Boyle's law, which tells us that volume and pressure are inversely related for a fixed temperature and for a fixed mass of gas. Remember what mass is? It's number of particles in a body, right? Like the number of moles. In our case, the number of moles is fixed to 1, and our temperature is also constant. So Boyle's law works here very well. Okay, if we want to calculate the smaller volume, then we must use then the larger pressure value. Pressure and volume are inversely related. Okay, so it's 1 mole times 8.314 joule per Kelvin per mole times the temperature, which is 298 Kelvin. Divide this by the pressure value, and we say the larger pressure value, which is 1 atmosphere. Okay, 1 atmosphere is the same thing as 1001325 pascals, which is the same thing as, let's put pascals. Pascals is the same thing as newtons per square meters. Okay, when you work that out, you'll get that V initial is something like 0.0244 meters cubed. Right? And I could just check that quickly. 8.314 times 298 times 1, of course, divided by 101,325. Yes, 0.0245. Okay, so I'm just going to put the 5 just to look a little better. All right. Let's see. 5 meters cubed. Okay. Mole here, cancel mole there, reciprocal Kelvin, cancel Kelvin there. And remember, joule comes from work, which is force times distance. Force is Newton times distance, which is meters. Okay, so Newton here, cancel Newton from there. 1 over the square of the reciprocal square of meters will give you meters cubed when you put this one with it. So you end up with meters cubed. The final volume, I could just by inspection, the fact that the pressure value, right, that we'll use to calculate the final volume is 10 times smaller than the initial pressure, I can tell you that the final pressure, the final volume will work out to be 0.2445 meters cubed. And you can try it. You can try it. Convert the 0.1 to newtons per square meters and put it in the formula, and you will see that this will be your final volume. Okay, now we have 2 volume values. Now we can go ahead and calculate the work. All right, let's just go over here. See that it's a little bit crowded. Work is equal to minus P delta V, just so you won't forget. So this works out to be the pressure that we'll be working with, right, is the 0.1, right, because that is where the volume started to expand. That is where the system was doing work. So 0.1, and I will convert that to newton per square meters. Okay, so that comes down to 101, and don't forget the minus sign, 32.5 newtons per square meters, yes, times the volume change, which would be something like final, which is 0.2445 minus 0.0245. 0.445, and that's meters cubed. Okay, that is what we have. And so I think our answer should work out to be about 2,200 and about 29. Let's see. And it's what you will have is reciprocal meter squared cancel this one. They end up with Newton meter, which is the same thing as joules. Let me just check that number. All right, let's just check our numbers. 0.2445 and 0.0245. Yes. Times. All right. Yes. Minus 2,229.6. All right. So let's just write that better. Um, Minus 2,229, let's say 0.65 joules. And remember, you'll get Newton meter, which is the same thing as joule. Now, we have calculated the work. The heat, right, is the same magnitude but opposite sign, 2,229.65 joules. Now, I would like to point something out, something that is important. If you recall, when we calculated the work for the reversible system, we got something like minus 5,704, recalling correctly, joules, right? And of course, the heat worked out the, of course, exact magnitude but opposite signs, all right? In this case, over here, over this side now, we work out to something like minus 2,229.65 joules, and Q worked out to be the exact magnitude, of course, but different signs. Now, look at what is going on here. Recognize that the reversible process is able to do more work, right, than the irreversible process. Just recognize that is what is important here. And even the PV curves can tell the story. Look, when we sketch the PV curve for the irreversible, we got something like this, changing from, what was that, 1 to 0.1, yeah? Okay, and V initial, V final, all right? And we said that, look, the area under the curve, all right? The area beneath the curve tells us the level of work that can be done. All right, so that's what we came up with. And this is what volume in meters cubed. Okay, now that's the irreversible. Look at the reversible. Look at what we came up with for the reversible system. Volume in meters cubed, V initial, V final, and this is the pressure, 1, 0.1 pressure in, let's say, atmospheres. For such a system, well, in this case, because we only have 2 points, it would appear to be like a line. But in reality, if we had more points, we would get a nice gentle curve. Anyway, look at the area beneath this curve. All right, look at the area beneath that. You see? Okay, the area beneath that curve tends to be large. All right, the area beneath that curve tends to be large. And even sometimes, well, you should really cut it off here, it will still work out to be large. Okay, So that is why well, not exactly why, but I'm saying that the PV curves actually gives you an indication. The PV curves actually give you an indication of the level of work. Just by inspection, just by looking at them, you can tell that a reversible system is able to do more work than an irreversible system. Okay? All right. Let's extend the discussion a little bit more. All right. This question also asks, what are the internal energy and enthalpy changes, delta U and delta H respectively, for the processes A and B described above? And the processes refer to the two calculations that we just did. Uh, the one concerning the reversible and that concerning the irreversible process. Now, first of all, both of them are isothermal. For isothermal processes, delta U is equal to zero. Firstly, all right, so that that you know has been taken care of already. Delta U is equal to zero for both processes. It doesn't matter if they are reversible or irreversible. The fact is that both of them are isothermal. Once you're dealing with isothermal, once you say isothermal, delta U is equal to zero, meaning that right, U final is equal to U initial. So if U final is equal to U initial, then clearly delta U must be equal to zero, seeing that delta U is equal to U final minus U initial. Okay, so that has been taken care of. Now, we're also asked about the delta H. We're also asked here about the delta H. Now, remember, delta H is equal to delta U, right, plus P delta V. Okay, yes, that's what that is equal. Now, delta U we just said is equal to zero. We just said that. So delta U is equal to zero. So delta H then works out to just be P delta V. That's what it works out for both cases, because both of them delta U is equal to zero. Now, right away, I can tell you that delta H, right, can do a better delta than that. Delta H is equal to well, let me just write this back. P delta V, which then is equal to 2229.65 joules. For both cases, how did I arrive at this? Earlier, we calculated delta V, right? And we said that delta V, of course, is equal to V final minus V initial. And we said that the final volume, right? The final volume was something like 0.2445. And when we subtract the initial volume, which was 0.02445, and both of these are meters cubed, all right? And then, of course, so that's delta V. This right here is delta V. And the pressure, right? The pressure was 0.1 atmospheres, all right? Which worked out to be in Newton per square meter to be 101.32.5 newtons per square meters. That's what it worked out to be. Okay? Now, remember, why did I use 0.1 atmosphere? It is at zero point 0.1 atmosphere that we looked at the expansion of the irreversible system. But then you're going to say to me now, oh, what about the reversible system? Now we're using this same pressure to discuss, such that we have common grounds to discuss both systems, right? because we can't discuss the irreversible system work concerning the irreversible system with the initial volume alone. There must be some sort of volume expansion for us to even talk about work. Okay? So we know we already calculated delta V, and we know the pressure at which there was this expansion for the irreversible system. And there was also expansion for the reversible system. And so that's why we use the 0.1. When we work that out, we got a value of 2,229.65 joules. Okay? For both systems, the delta H is the same, of course. How can that be? We're talking about an irreversible versus a reversible system. So we're talking about irreversible versus reversible. So how is it possible that they have the same delta H? Remember, delta H is a state function. The only thing that matters is the final state and the initial state. These are the two things that matter for state functions. Not how you got there, not whether or not whether you change your pressure from 1 to 0.1 and then you expand. Delta H doesn't care about that. Delta H is concerned with, well, what was your initial state? Okay, what is your state now? Just final and initial. It doesn't care about the in-between. And guess what? For a irreversible system, PV is equal to nRT at the beginning and at the end. That is at the final and at the initial stages. Also, guess what again? For a reversible system, PV is also equal to nRT at the beginning and at the end. It is for a reversible system, PV is also equal to nRT all throughout. What I'm saying to you is that an irreversible and a reversible system are identical at the beginning and at the end. That is at the initial stages and at the final stages. Where they differ is in between the initial and the final. One of them is at equilibrium all the time, whether it be at the beginning, in the middle, at the end. That one is called the reversible. The irreversible, right, is only at equilibrium at the beginning and at the end. This tells you a story. Both of these systems are identical at the beginning and at the end. And that is why, right, delta H for both of them will be the same, because delta H is only concerned with the final and initial stages.